Let us talk about this problem. We are given an array and a number d. We need to left rotate this array by d. In this array, we are given array as 1, 2, 3, 4, 5 and d is given as 2. So when we left rotate it by 2, please remember left rotate means counterclockwise rotation. So all these elements go to 2 positions back. This goes to 2 position back. This goes to 2 position back. Please note that these 2 elements do not have anything on left side and they go 2 positions back in circular manner. So 1 goes here, right? 1 position back is 5 and 2 position back is 4. And 2 goes here. 1 position back is 1 and 2 positions back is 5 in circular manner. And that's what we call left rotation. In this array, we need to rotate this array by 3. So 15 comes here, 3 positions back. And these elements go 3 positions back in circular manner. So this 10 goes here, 5 goes here, and 30 goes here. Right? 1, 2, 3, 3 positions in circular manner, in counterclockwise manner. Please pause this video and try to think of a solution for this problem. We are going to talk about 3 different solutions. The first solution is going to be theta n into d. Then we are going to talk about a solution which is theta n but requires theta d extra space. Then we are going to talk about third solution which is theta n and requires theta 1 extra space. In all the solutions, we may assume that d is smaller than or equal to the number of elements in the array. However, we can extend this question when d is greater than number of elements in the array also. But all we need to do in that case is we need to subtract n from d. So whenever d is greater than n, you can simply subtract n from d and you can get the effective number of rotations. Please note that if you're rotating an array of size 4 by 4, it becomes the same array. And if you're rotating an array of size 4 by 5, it effectively is rotation by 1. Let us now talk about a naive solution to rotate an array by d. We have already discussed rotate by 1 in the previous video. We can simply call left rotate by 1 d times and we get the left rotation by d. So this is the function we already discussed in detail in the previous video. What happens here? We left rotate the array by 1. So if you want to left rotate the array by 2, you first left rotate it by 1. So your array becomes 2, 3, 4, 5 and then 1 after first left rotation. Then you again left rotate it by 1. And this time your array becomes 3, 4, 5, 1, 2. So you have left rotation by 2 by simply calling left rotate by 1 2 times. If you want to left rotate by 3, you will call left rotate by 1 3 times. And how does this work? This function simply copies the elements starting from second element to 1 position back. So second element is here. This copies this to here. Array I minus 1 equal to array I. This to here, this to here, this to here, and there's nothing after it. So at the end, it copies the temp element, which is the first element, to the end. So this element is copied to here. That's how left rotate by 1 happens. And if we call it d times, we get the left rotate by d. The time complexity of this solution is d into theta n. We have theta n operation and we are calling it d times. So it's theta n d time. And auxiliary space required by the solution is theta 1 because we are not using an auxiliary array. Now please pause this video and think of a solution that works in theta n time. You may first try a solution that takes theta d extra space, then try a solution that takes theta 1 extra space. Let us now talk about a better solution to solve the problem. The idea is simple. We first copy the first d elements into a temporary array. It is similar to left rotate by 1 actually. There we were copying the first element into a temp variable. Here we copy the first d elements into a temporary array. So we create a temporary array and copy the first d elements. And that's what our temporary array contains. D is 2. So we copied the first 2 elements. After that, like the left rotate by 1 solution, we were shifting every element toward the left one time, 1 position back. Here we will be shifting every element d positions back. So what we do is we move this element here and we move this element here and we move this element here 2 positions back because d is 2. Please note that we do this shifting from index d, which means d plus 1th element, because for first d elements there is nothing d positions back. So we still need to handle these 2 elements. We need to left rotate them in circular manner. 1 should come here, 2 should come here. That's what we actually get after rotating the n minus d elements. Now we need to rotate the d elements. For that, we run one more loop. And inside the loop, we copy the elements from temp to ARR. Now temp index is clear. We need to copy the d elements of temp. So index should be I from 0 to d minus 1. What should be the index here? This index we got as n minus d plus 1. You can notice that first element of temp comes here at this position and second element comes here at this position. And what is this position? This is n minus d. And what is this position? This is n minus d plus 1. What is n? N is the number of elements in the array, which is 5, and d is 3. So this particular position or index is 3 and this index is 3 plus 1, 4. Now what is the time complexity of the solution? This particular operation requires theta d time. This operation requires theta n minus d time. And this again requires theta d time. So the overall time complexity is theta d plus n minus d plus d, which is theta of n plus d. Since we know that d is smaller than or equal to n, we can ignore it. So our time complexity is theta n. Now what is the auxiliary space requirement for this? We are using an auxiliary array of size d. So theta n time and theta d auxiliary space. Now please think of a solution that works in theta n time and takes theta 1 auxiliary space. Let us now talk about third solution to rotate an array. This solution is mainly these 3 steps. This is what this solution is all about. We have an extra reverse function which is being called here. This reverse function is simply taking low indexed and high indexed and reversing the array between these 2 indexes, including the 2 indexes. So this algorithm says that first reverse the first d elements. Index 0 to d minus 1 means first d elements. Then reverse the remaining n minus d elements from index d to n minus 1. Then reverse the whole array. And you get the rotated array. Let's see how does this work. So here is an example. We have an array of 5 elements as we have shown there, and d is 2. So first we reverse these 2 elements. And after reversing we get this 2, 1. And these 3 elements remain as it is. Because for the reverse function we are passing the parameters as 0 and d minus 1. Then we reverse the last 3 elements. And after reversal we get this. So this happens after the second reversal. After that we reverse the whole array. And after reversing the whole array we get 3, 4, 5, 1, 2. And you can notice that you have the rotated array. This array is left rotation of the original array by 2. This is same as your expected output array. Let us now talk about time complexity of the solution. This solution does reverse for an array of size d. So we have theta d work. Then it does reverse for an array of size n minus d. So we have n minus d work here. Then it does reverse the whole array. So we have n work here. And if we do sum of all these, we get 2n, theta 2n, which is theta n. So time required by this algorithm is theta n, and auxiliary space required by the solution is theta 1.